Two galaxies are approaching each other. Each one contains hundreds of billions of stars. Each one spans hundreds of thousands of light years. Each one has been traveling through the void for billions of years, pulled by the other's gravity, across a distance that dwarfs any scale we normally use to measure things, across millions of light years of space. Accelerating toward each other at hundreds of kilometers per second, the approach so slow in human terms that it would be invisible to any observer watching in real time. And then, over hundreds of millions of years, they collide. Except that, collide is almost the wrong word, because what happens is both more violent and more ghostly than any ordinary collision you have ever witnessed. Two structures made mostly of empty space pass through each other. Most of the stars never touch. And yet the galaxy is transformed so completely, its shape, its chemistry, its star formation rate, its central black hole, the orbits of every star it contains, that nothing about it afterwards resembles what it was before. Galaxies do not collide the way cars collide. They collide the way two orchestras might collide, each instrument still playing, but the music utterly changed. If you enjoy videos that take the most dramatic events in cosmic history and work through them with physical precision, that refuse to hand-wave over the details and instead sit with the actual numbers and the actual mechanisms, I genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. The most common misconception about galaxy collisions is that they are primarily destructive, that galaxies slumming into each other is catastrophic, in the way a car crash is catastrophic, leaving wreckage behind, destroying stars, sterilizing planets, obliterating the structures that existed before. People imagine the stars of two galaxies crashing into each other, explosions across billions of light years, a cosmic catastrophe. This picture is wrong in almost every particular. Galaxy collisions are not primarily destructive, they are primarily creative. They are among the most productive events in the universe, triggering the formation of new stars at rates that can exceed anything achievable in isolation, building new structures, driving the evolution of galaxies from one type to another, feeding the supermassive black holes at galactic centers, and ultimately assembling the large elliptical galaxies that dominate the cores of galaxy clusters. The universe builds its largest structures through collision, not despite collision. And understanding why the collision is creative rather than merely destructive requires understanding the fundamental architecture of a galaxy, what it is mostly made of, and what it is mostly not made of. Begin there. Begin with the emptiness. A galaxy is an almost unimaginably sparse structure. Our own Milky Way contains something between 200 billion and 400 billion stars, occupying a disk roughly 1,000 light-years in diameter and about 1,000 light-years thick at the Sun's location. The stars are not uniformly distributed through this space. They are concentrated in the spiral arms, in the central bulge, in the thin disk, but even in the densest regions, the average distance between stars is measured in light-years. At the Sun's location, the nearest star to our Sun is Proxima Centauri. At about 4.24 light-years, the diameter of the Sun is about 1.4 million kilometers, roughly 0.47 light-years. The distance to the nearest star is almost 1 billion times the diameter of the Sun itself. To put that emptiness in a tactile form, if you shrank the Sun to the size of a grapefruit, about 12 centimeters across, Proxima Centauri would be, at the same scale, another grapefruit sitting roughly 3,200 kilometers away. The distance from London to the Himalayan foothills, 2 grapefruits separated by the width of a continent, and the space between them completely empty. No planets, no asteroids, no gas worth mentioning, just void. This is what a galaxy is. Mostly void, overwhelmingly void. The stars are the raisins in a bread whose dough is nothingness. When two such structures approach each other and begin to overlap, the probability of any two stars physically colliding is extraordinarily small. Run the numbers. In the Milky Way, the cross-sectional area of the Sun is approximately 1.5 times 10 to the power of 18 square meters. The disk of the galaxy, in cross-section perpendicular to the galactic plane, has an area of roughly 3 times 10 to the power of 322 square meters. The filling factor, the fraction of that cross-section actually occupied by the solid disks of stars, is on the order of 1 part in 10,114, 1 part in 100 trillion. If you fired a bullet at random through the Milky Way's disk, the probability of hitting any star would be roughly 1 in 100 trillion. The same probability applies to a star in an approaching galaxy moving through the disk of the Milky Way. Its chance of physically striking any Milky Way star is approximately 1 in 100 trillion. Two galaxies, each with hundreds of billions of stars, moving through each other, the expected number of direct stellar collisions is perhaps a handful, if any, in the entire merger event. The stars essentially ignore each other as physical objects. They pass through the combined structure like two clouds of smoke drifting through each other, interpenetrating without collision, their individual particles never touching. This is the first and most important fact about galaxy mergers. The stars do not crash. The stars dance. But before the stars begin to dance, there is a larger structure that is already interacting, the dark matter halo. Each galaxy is embedded in a dark matter halo that is far more massive and far more spatially extended than the luminous galaxy at its center. The Milky Way stellar disk contains something like 50 to 60 billion solar masses of stars, but the total mass of the Milky Way, including its dark matter halo, is approximately 1 trillion solar masses, perhaps more. The dark matter constitutes roughly 95% of the galaxy's total mass, most of it spread through a roughly spherical halo extending hundreds of thousands of light years beyond the visible disk in every direction. Andromeda has a similar structure, with its own dark matter halo of comparable mass. When two galaxy-bearing dark matter halos approach each other, the halos begin to interact gravitationally, long before the visible galaxies come within range of each other. Dark matter halos are diffuse, extended structures, and two halos of galaxy-scale mass begin to overlap when the galaxies are still separated by hundreds of thousands of light years, when the luminous portions of the galaxies are not yet visibly distorting each other. The dark matter halos, being collisionless just like the stars, interpenetrate without direct collision. But unlike the stars and the disks, which are mostly concentrated in a thin, flat structure, the halo dark matter is distributed in 3 dimensions, and the gravitational interaction between the two halos provides the initial dynamical context for the entire merger. The orbit of one galaxy through the combined dark matter potential of both halos determines the trajectory of the encounter, the timescale of the merger, and the efficiency of dynamical friction. The dynamical friction that eventually causes the orbit to decay and the two galaxies to merge acts primarily on the dark matter halos, not on the stellar disks. The halos are massive and extended, and as one moves through the other, the gravitational wake effect is most pronounced in the large-scale dark matter distribution. This is why N-body simulations of galaxy mergers, which were initially run without dark matter, using only the stellar masses, systematically underestimated the efficiency of orbital decay. Including realistic dark matter halos, with their much larger total masses and much larger spatial extents, dramatically accelerates the merger timescale by increasing the efficiency of dynamical friction. The dark matter halos also protect the stellar disks during the early passes. Because the halos are so much more extended than the disk, the first close pass of two galaxies may bring the halos into deep overlap, while the stellar disks are still separated by a significant distance. The gravitational interaction during this pass primarily affects the orbital trajectories of the two systems, without yet producing the violent gas shocks and tidal distortions that accompany close disk-disk encounters. The halo-halo interaction is a kind of cosmic braking system, dissipating orbital energy through dynamical friction and bringing the galaxies back together for the next, closer pass that will involve the disk-disk encounter. Without dark matter halos, galaxies would be far less effective at merging. They would need far more direct encounters to lose enough orbital energy for coalescence. With dark matter halos, even a relatively glancing encounter can lead to eventual merger, as the halos trap the two galaxies in a decaying neutral orbit. There is another role dark matter plays in a merger that is less often discussed but equally important. It determines the shape of the gravitational potential that stars and gas must navigate during the collision. As the two halos interpenetrate and begin to merge, the dark matter distribution provides the deep potential wells that organize the flow of gas during the merger. The gas does not fall freely and uniformly toward the galactic centers. It flows along the filaments and ridges of the dark matter potential, channeled by structures invisible to any optical telescope. The star formation that erupts in a merger is not random across the merged gas disk. It is organized, concentrated in regions where the dark matter potential channels gas most efficiently, where the shocks are most intense, where the genes instability is most readily triggered. The beautiful imagery of merging galaxies, the bright knots of starburst activity, the interspersed dark lanes of obscuring dust, the luminous arcs and streams, all of it is the luminous tracery of processes organized by the underlying dark matter skeleton. We cannot see dark matter. We infer its presence from its gravitational effects, the rotation curves of spiral galaxies that remain flat at large radii when they should decline, indicating the presence of additional unseen mass. The gravitational lensing of background galaxies by foreground clusters, revealing mass distributions far more extended than the visible light. The large-scale structure of the cosmic web, whose filaments and voids match the predictions of dark matter simulations to extraordinary precision. But in galaxy mergers, the dark matter is not merely an inert background. It is an active participant, organizing the dynamics, setting the timescale, and shaping the outcome. The visible drama of a galaxy collision, the tidal tails, the starbursts, the quasar flare, is, in a deep sense, the visible expression of processes organized by the invisible majority of the matter involved. But gravity has very long arms. Even if two stars never come close enough to collide, the gravitational field of an approaching galaxy, a field produced collectively by hundreds of billions of stars, dark matter, gas, and dust, reaches across millions of light years and begins distorting the orbital paths of stars in the target galaxy long before the first star of the approaching galaxy enters the disk. The disruption begins not with collision, but with tidal forces, and these tidal forces produce some of the most spectacular structures in the observable universe. The first visible sign of an approaching galaxy merger is the tidal destruction. Just as the moon's gravity raises tides in Earth's oceans by pulling the near side of the ocean more strongly than the far side, a passing galaxy raises tidal destructions in the galaxy it is approaching. The near side of the galaxy is pulled more strongly toward the intruder than the far side, stretching the galaxy along the line connecting the two centers of mass. Simultaneously, the galaxy is compressed perpendicular to this line, as the near and far sides are drawn together relative to the center. The result of these tidal forces, which act on the stellar orbits that normally keep the galaxy's shape stable, is the creation of tidal tails and bridges. Tidal tails are long, thin streams of stars and gas drawn out from the galaxy's disk along the direction of the encounter, curving gracefully into intergalactic space. Tidal bridges are streams of material connecting the two galaxies as they pass, pulled from each by the gravity of the other. These structures can extend for hundreds of thousands of light years, as long as or longer than the galaxies themselves, and they persist for hundreds of millions of years after the initial close passage, slowly dispersing as the stars within them follow their modified orbits. The canonical example of this tidal distortion, the image that has made galaxy mergers one of the most visually striking phenomena in all of astronomy, is the Andromeda Galaxies, designated NGC 4038 and NGC 4039. Two spiral galaxies in the constellation Corvus, currently in the process of merging, the antennae are named for the two vast tidal tails that extend outward from the collision site in opposite directions, curving away from each other like the antennae of an insect. These tails, each stretching roughly 100,000 light years into intergalactic space, are composed of billions of stars that were in the outer disks of the original spiral galaxies before the tidal forces of the encounter drew them out and deposited them into these magnificent arching streams. The antennae are approximately 45 million light years away, close enough for the Hubble Space Telescope and the James Webb Space Telescope to resolve individual star-forming regions within the merger zone, and they provide the most detailed observational study of an ongoing galaxy merger currently available. What Hubble and Webb have revealed in the antennae is extraordinary. The collision zone, the region where the two galactic disks are overlapping, is a blazing factory of star formation. Hundreds of bright young star clusters are visible, each one containing hundreds of thousands to millions of new stars born in the last few tens of millions of years, glowing blue-white with the fierce light of massive young stars that will live only a few million years before exploding as supernovae. The star formation rate in the antennae is approximately 20 times higher than the star formation rate of the Milky Way today, a burst of stellar birth triggered directly by the collision, driven by a mechanism we will explore in detail. The antennae are not dying, they're giving birth. The collision is not destruction, it is a prolific, violent, luminous creation. To understand why collisions trigger star formation rather than suppressing it, you need to understand the difference between stars and gas, and specifically, why it is the gas and not the stars that makes the collision creative. Stars, as we have established, are essentially collisionless during the galaxy merger. They pass through the merged structure under the influence of gravity alone, their orbital paths modified, but their physical integrity unaffected. Gas is different. Gas is a compressible, dissipative medium that can collide, shock, radiate energy, and collapse. When the gas disks of two spiral galaxies interpenetrate, the gas does not pass through cleanly the way the stars do. It collides. Gas clouds from one galaxy smash into gas clouds from the other at relative velocities of hundreds of kilometers per second. The collision produces shock waves, regions of compressed, heated gas, where the kinetic energy of the bulk flow is converted to thermal energy. In the shock, the gas is compressed to densities far higher than in the pre-collision interstellar medium, and high-density gas, under the right conditions, is precisely the precondition for star formation. Star formation in normal galaxies occurs when a region of interstellar gas, a molecular cloud, a dense accumulation of hydrogen and helium and trace amounts of heavier elements, reaches a mass sufficient that its self-gravity overwhelms the thermal pressure, turbulence, and magnetic fields that would otherwise prevent collapse. This threshold is described by the Jeans criterion. A molecular cloud collapses if its mass exceeds the Jeans mass, which depends on the temperature and density of the gas. The higher the density, the lower the Jeans mass, meaning that denser gas collapses at lower mass thresholds, producing more collapse events per unit volume. The shocks produced in a galaxy-galaxy collision do exactly this. They compress the gas to higher densities, lowering the Jeans mass threshold and triggering collapse across enormous volumes of gas that were stable in their pre-collision state. The collision acts as a cosmic trigger, pressing the gas over the threshold from stable to unstable, initiating a cascade of star formation that produces the brilliant bursts of blue-white light visible in merging systems like the antennae. This process is called a starburst, and it is one of the most spectacular phenomena in observational astrophysics. A starburst galaxy, one undergoing a dramatically elevated rate of star formation, can produce new stars at rates of 10 to 1,000 times the normal rate for a galaxy of its size. The most extreme starbursts, found in the most violent mergers in the most gas-rich galaxies, can form stars at rates of hundreds to thousands of solar masses per year. Our Milky Way currently forms stars at a modest rate of about 1 to 2 solar masses per year. A starburst at 100 times this rate would produce, in a single year, as much new stellar mass as the Milky Way produces in a century. In the most extreme ultra-luminous infrared galaxies, the ULIRGs, which are invariably merger systems, observed during or shortly after a close encounter, star formation rates exceed 1,000 solar masses per year, and the total infrared luminosity radiated by the heated dust surrounding these star-forming regions can exceed the luminosity of an entire normal galaxy by factors of hundreds. The observational discovery of UIRGs is itself a story worth telling, because it reveals how a new wavelength range can transform our understanding of what the universe contains. In 1983, the Infrared Astronomical Satellite, IRAS, the first space telescope to survey the entire sky at infrared wavelengths, detected thousands of sources radiating extraordinary amounts of energy in the infrared. The most luminous of these, the ultra-luminous infrared galaxies, with infrared luminosities exceeding 10,000, 12 times the Sun's luminosity, were initially mysterious. They were too bright to be normal galaxies, too numerous to be quasars, and their infrared emission suggested they were surrounded by enormous amounts of warm dust that was absorbing and re-radiating stellar and AGN emission. Spectroscopic follow-up observations revealed that nearly every ULRG was a merging galaxy system, a pair of gas-rich spiral galaxies in the process of a close encounter, their gas disks colliding and driving a prodigious starburst. The heat from the thousands of hot young stars in the starburst, and sometimes from an obscured AGN, was absorbed by the dust pervading the collision zone and re-radiated at infrared wavelengths. The dust made the starburst nearly invisible at optical wavelengths. The same dust that makes the merger beautiful in the optical, with its dark lanes and bright knots, was also making the most luminous aspect of the merger invisible to optical telescopes. The discovery of ULIGs revealed a population of objects whose total energy output was not being captured by optical surveys. The universe's most luminous merging systems were shrouded in dust and could only be seen by those willing to look at infrared wavelengths. This had immediate implications for the cosmic star formation history, the rate at which new stars were formed throughout the universe as a function of time. Optical surveys of high redshift galaxies, looking at the rest frame ultraviolet emission from hot young stars, were underestimating the total star formation rate because they missed the dust-obscured component. Infrared and submillimeter surveys, sensitive to the thermal emission of the heated dust, revealed a population of submillimeter galaxies, high redshift analogues of local ULIRGs, that were forming stars at rates of thousands of solar masses per year, utterly invisible in the optical, but blazing in the submillimeter. The inclusion of this dust-obscured star formation significantly boosted estimates of the cosmic star formation rate at redshifts of 1 to 3, exactly the epoch when the merger rate was highest and when the universe was assembling most of its stellar mass. The James Webb Space Telescope, with its exquisite infrared sensitivity and spatial resolution, has begun to peer into the hearts of these dusty starburst systems with a clarity not previously possible. Resolving individual star-forming clumps within merging systems, measuring the ages and masses of the superstar clusters born in the starbursts, and tracing the complex interplay of star formation and AGN activity in the most luminous systems. JWST observations of the antennae have resolved hundreds of young star clusters in the overlap region, revealing that the most massive clusters, objects containing millions of young stars, as massive as globular clusters, are preferentially located in the regions of highest gas density, exactly where the collision-driven compression is most intense. The starburst is not happening uniformly across the merging system. It is concentrated in the shock zones, organized by the physics of the gas-gas collision, producing the most massive star clusters in the local universe in the exact locations where the collision dynamics predict it should. The agreement between theory and observation is striking. But starburst-driven star formation, for all its prodigious output, is a temporary phenomenon. The gas is a finite resource. Forming stars depletes the molecular gas reservoir. The massive stars born in the starburst live brief lives, a few million years, and explode as supernovae, injecting energy and momentum back into the surrounding gas, heating it, disrupting the molecular clouds that were the nurseries of the next generation and effectively suppressing further star formation through what is called stellar feedback. A starburst ignites, blazes brilliantly for tens of millions of years, then fades as the gas is consumed or dispersed. The aftermath is a galaxy with a stellar population enriched by the starburst, containing billions of stars born in the merger, but with less gas available for future star formation than either progenitor galaxy had before the encounter. The timescale of a galaxy merger, from first tidal distortion to final coalescence into a single object, is itself something that needs to be made concrete. Because the numbers involved challenge the imagination, and because different stages of the merger have fundamentally different character, the timeline deserves careful attention. The approach phase is the longest. Two galaxies can begin gravitationally influencing each other while still separated by millions of light years. As they fall toward each other under gravity, they accelerate. A typical approach velocity, the speed at which two galaxies are moving toward each other before they become gravitationally bound to each other, is a few hundred kilometers per second. At 300 kilometers per second, closing a gap of 1 million light years takes about 1 billion years. The approach is glacially slow by any ordinary standard. And because the galaxies are also orbiting each other, because the encounter is almost never a head-on plunge, but rather a trajectory with some angular momentum, the first pass is usually not a merger, but a close flyby. A first encounter in which the two galaxies sweep past each other at close range, tidally distorting each other and flinging out tidal tails, then separating and swinging back around for a second pass. Then a third. The orbital energy of the system is gradually dissipated through dynamical friction, the gravitational drag that acts on a massive object moving through a sea of lighter objects. In this case, the drag exerted on each galaxy by the stellar distribution of the other, until the orbit decays enough that the two galactic nuclei can finally merge. The total duration from first tidal distortion to final nuclear coalescence is typically 1 to several billion years. The antennae, currently in their first or second pass, will not complete their merger for another few 100 million years. The Milky Way, which will collide with the Andromeda Galaxy in approximately 4.5 billion years, a merger we will return to in considerable detail, will not complete its merging process until roughly 6 to 8 billion years from now, when the two galactic nuclei finally coalesce. The stars currently in both galaxies will have spent most of the merger period orbiting in the combined tidal field. Their individual identities as Milky Way stars or Andromeda stars gradually lost as dynamical processes mix the two populations into a single new structure. Not all galaxy mergers are the same. The nature of the collision, its outcome, its violence, its visual appearance, the structures it creates, depends on several key parameters: the mass ratio of the two galaxies, their gas fractions, their relative velocities, the angle of their approach, and the orientation of their spin axes relative to the orbital plane of the encounter. Each of these parameters produces different physics and different observational signatures, and understanding the full range of merger types is essential to appreciating the variety of galaxy morphologies we observe in the universe. A major merger, sometimes called an equal mass merger or a 1-1 merger, though in practice any mass ratio up to about 1/4 is typically included in this category, is the most dramatic type of encounter. Two galaxies of comparable mass approach each other. Their tidal forces are of comparable strength, and the outcome is the most complete scrambling of both galaxies' structures. Major mergers are the most efficient at converting spirals into ellipticals, triggering the most powerful starbursts, and inducing the most intense AGN activity. The antennae are a major merger, with the two progenitor spirals of comparable mass. The Milky Way Andromeda collision will be a major merger, with mass ratios of roughly 1 to 2, placing it at the boundary between major and minor. A minor merger, a 1 to 4 to 1 to 10 mass ratio, or even smaller, produces very different results. A small galaxy falling into a large one is more likely to be tidally disrupted and absorbed without fundamentally transforming the large galaxy's structure. The satellite is stretched and shredded by the tidal forces of its host, depositing its stars into the outer halo and thick disk of the primary galaxy. The primary galaxy may show tidal streams, minor morphological disturbances, and modest enhancement of star formation, but its disk structure often survives largely intact. This is how the Milky Way has been growing throughout its history, through the absorption of dwarf galaxies and satellite galaxies, each one contributing its stellar population to the halo, but not disrupting the disk. The Sagittarius dwarf spheroidal galaxy, currently in the process of being tidally disrupted by the Milky Way's gravity, is an example of an ongoing minor merger. Sagittarius is being stretched into a stellar stream that wraps around the Milky Way multiple times, its stars being progressively incorporated into the Milky Way halo without any significant disruption to the Milky Way disk. Prograde versus retrograde encounters are another crucial variable. A prograde encounter is one in which the orbital angular momentum of the encounter, the angular momentum of the orbit of one galaxy around the other, is in the same direction as the spin angular momentum of one of the galaxy's disks. A retrograde encounter has these angular momenta in opposite directions. The difference is dramatic. In a prograde encounter, the tidal forces are in resonance with the disk's rotation, producing much stronger tidal distortions, longer, more prominent tidal tails, more efficient mass ejection, more dramatic morphological disturbance. In a retrograde encounter, the resonance condition is not met, and the tidal effects are significantly weaker. This is why the two galaxies in an encounter often look strikingly different from each other. Even if their masses are comparable, the galaxy whose disk is in prograde orientation to the encounter may develop spectacular tidal tails, while the other, in retrograde orientation, shows much less disturbance. Ring galaxies, one of the most striking and exotic of galaxy morphologies, are produced by a specific type of encounter in which a smaller galaxy passes nearly directly through the center of a larger galaxy, perpendicular to the disk plane. The intruder, moving through the disk center, sends a radially outward density wave propagating through the disk like a ripple on a pond. This ring wave sweeps up gas as it propagates outward, triggering star formation along its leading edge and producing the characteristic ring of luminous blue star clusters that gives these objects their name. The Cartwheel Galaxy in the constellation Sculptor, a nearly perfect ring galaxy about 500 million light-years away, observed in detail by both Hubble and the James Webb Space Telescope, is the most famous example. Its outer ring, about 150,000 light-years in diameter, is a blazing circle of young blue stars. Its inner structure shows the distorted remnant of the original disk, and the companion galaxy responsible for the collision is visible nearby. Having punched through the disk center and continued outward, leaving behind the expanding ring. Ring galaxies are short-lived. The ring continues to expand and eventually disperses, and rare, requiring the specific geometry of a near-central impact. But they represent one of the universe's most spectacular demonstrations of the creative power of collision, a galaxy whose central disk has been turned inside out. Its star formation organized into a perfect geometric ring by the passage of a compact intruder. Polar ring galaxies present another exotic variant. In these systems, a ring of stars and gas orbits the central galaxy in a polar orbit, nearly perpendicular to the main disk. These structures are thought to form when a smaller galaxy approaches in a polar orbit and is tidally disrupted, with its material settling into the polar plane of the interaction. The result is a galaxy with two distinct structural components orbiting in perpendicular planes, the main disk and the polar ring, each visible simultaneously in images, and creating a three-dimensional structure that reveals the shape of the prey. Galaxies' dark matter halo directly, since the precession rate of the polar ring depends on the flattening of the dark matter potential. Polar rings are therefore not just exotic morphological curiosities, but physical probes of dark matter distribution, using the orbital dynamics of tidally acquired material to infer the shape of the invisible dark matter halo. This is one of the many examples in astrophysics where an apparently exotic phenomenon turns out to be a precision measuring instrument for something that cannot be directly observed. The history of understanding galaxy mergers as a process is also worth recounting, because it is a story of theoretical prediction eventually vindicated by observation, a story in which the key insights came from computation at a time when observations were not yet sensitive enough to fully reveal the phenomenon. In the 1970s, Alaa and Jiri Tulmuri, brothers and astrophysicists at MIT and New York University respectively, performed some of the earliest numerical simulations of galaxy-galaxy encounters. Their landmark 1972 paper, Galactic Bridges and Tails, presented n-body simulations of restricted three-body problems, simulating the response of test particles in one galaxy to the gravitational pull of a passing companion, computed on the computers of the era, and showed that the tidal tails and bridges observed in systems like the antennae and the mice could be naturally explained by simple gravitational dynamics, without any need for exotic physics or magnetic fields or other special mechanisms. The shapes of the tidal tails, their curvature, their extent, their orientation, were direct consequences of the geometry and velocity of the encounter, and by matching simulations to observations, the Tulmurs were able to reconstruct the orbital parameters of the encounters and demonstrate that the tidal debris was a natural outcome of gravity acting on a differentially rotating disk. The Tulmur paper is now recognized as one of the founding documents of computational astrophysics, the first demonstration that numerical simulations of stellar dynamics could not just reproduce, but explain observed astronomical morphology. In the intervening 50 years, n-body and hydrodynamic simulation capabilities have advanced by many orders of magnitude. Hardened simulations, like the Illustris T&G, Eagle, and Horizon AGN cosmological simulation suites, follow the formation and evolution of millions of galaxies through cosmic time, tracking not just the gravitational dynamics of the dark matter and stellar components, but also the hydrodynamics of the gas, the formation and feedback of stars, and the growth and feedback of supermassive black holes. These simulations reproduce the observed properties of galaxy populations across cosmic time with remarkable fidelity. The galaxy mass function, the color magnetodiagram, the correlation between black hole mass and galaxy bulge mass, the star formation history of the universe, the morphological mix of spirals and ellipticals at different redshifts, all emerge naturally from simulations that apply known physics to cosmological initial conditions. The simulations confirm, in detail, the picture of galaxy mergers as the primary driver of galaxy transformation. They show spirals becoming ellipticals through major mergers, They show starbursts triggered by gas-rich encounters. They show AGN feedback quenching star formation. They show the hierarchical assembly of galaxies from small to large. The physics of galaxy mergers, first glimpsed in the simplified simulations of the two mirrors, has been validated by half a century of computational astrophysics. Dynamical friction deserves explanation because it is the mechanism that turns what would otherwise be endless orbital motion, two galaxies orbiting each other forever, never merging, into the eventual coalescence we observe. When a massive object moves through a distribution of lighter objects, the gravitational interaction between the massive object and the lighter ones creates a slight over-density of lighter objects behind the massive object, a gravitational wake, pulled into existence by the massive object's gravity and trailing behind it as it moves. This overdense wake exerts a gravitational pull on the massive object, directed backward along its trajectory, decelerating it. The energy lost by the massive object to this gravitational wake is transferred to the lighter objects, which gain kinetic energy, a process called dynamical friction, or Chandrasekhar dynamical friction, named after the Indian-American astrophysicist Subramanian Chandrasekhar, who first described it mathematically in 1943. In a galaxy merger, dynamical friction acts on each galaxy as a whole as it moves through the combined gravitational field of the other, and more importantly, it acts on the dense central regions, the galactic nuclei and their supermassive black holes, as they orbit within the newly assembled merged stellar system. Once the two galaxy disks are fully interpenetrated, and the stars are orbiting in the combined potential, the two supermassive black holes find themselves separated by tens of thousands of light years, orbiting in the sea of stars. Dynamical friction efficiently transfers orbital energy from the black holes to the surrounding stars, hardening the binary, bringing the black holes closer and closer together, on a timescale of hundreds of millions to billions of years. This is the process by which supermassive black hole binaries form in galaxy mergers, and it is directly relevant to one of the most anticipated discoveries of the next decade of gravitational wave astronomy. The detection of gravitational waves from merging supermassive black holes. The fate of the supermassive black holes in a galaxy merger is one of the most actively studied problems in theoretical astrophysics, and it deserves attention here because it represents, perhaps, the most consequential legacy of the collision. Every large galaxy contains a supermassive black hole at its center, a black hole with a mass ranging from millions to billions of times the mass of the Sun, sitting in a dense nuclear star cluster at the galactic nucleus, exerting gravitational influence over the stellar orbits in the inner few thousand light years of the galaxy. The Milky Way central black hole, Sagittarius A, has a mass of about 4.15 million solar masses. Andromeda's central black hole is considerably more massive, perhaps 100 million solar masses, though the precise value is debated. When the Milky Way and Andromeda merge in 4.5 billion years, these two black holes will eventually find themselves orbiting each other in the merged system, their separation decreasing under dynamical friction until they are separated by a parsec, about 3.26 light years or less. What happens when two supermassive black holes approach this close separation is a matter of intense theoretical interest and observational search. At separations of parsecs to tens of parsecs, dynamical friction from the stellar background efficiently brings the black holes together. But at smaller separations, the hardening phase, when the binary is compact enough that the individual stellar interactions that provide the dynamical friction become rare, the inspiral slows dramatically. This is the final parsec problem. This is the feature in spiral, the theoretical difficulty of bringing two supermassive black holes from parsec separations to the sub-milliparsec separations at which gravitational wave emission becomes efficient enough to drive the remaining in spiral to coalescence. Whether the final parsec problem is a genuine barrier to merging, or is resolved by processes like eccentricity, gas-driven in spiral, or stellar population effects, is still debated. What is clear is that eventually, either through one of these processes or through some combination, the black holes do merge. The observational evidence: the universe contains far fewer supermassive black hole binaries at close separations than expected if mergers stalled at the final parsec, suggesting that the mergers do complete on timescales complicated to the time between galaxy mergers. When two supermassive black holes finally coalesce, after perhaps billions of years of orbital decay, they emit a burst of gravitational waves so powerful that it briefly outshines the entire electromagnetic output of the universe. The gravitational wave energy emitted in the final seconds of a supermassive black hole merger, as the two event horizons touch and the two singularities, or whatever quantum gravity replaces them, merge into one, is comparable to the rest mass energy of the entire merged black hole, a fraction of which is radiated away in gravitational waves. To the first thinkers of the entire merged black hole, this merge is not the first thinkers of the entire merged black hole. What is the content called? Do you see the set of science patterns on? Do you see a single half-sized element of the entire merged black hole? This merge to some kind of time symbol is not the first thing called. The total energy output of the Sun over its entire 10 billion year lifetime is roughly 10,444 joules. The gravitational wave energy of a supermassive black hole merger exceeds the Sun's lifetime energy output by 16 orders of magnitude, one followed by 16 zeros. This is not a hypothetical future discovery. Pulsar timing arrays, networks of precisely monitored millisecond pulsars scattered across the galaxy, whose pulse arrival times are sensitive to the passage of gravitational waves, have already detected the gravitational wave background produced by the population of supermassive black hole mergers throughout the universe's history. In 2023, multiple independent pulsar timing array collaborations announced evidence for this nanohertz frequency gravitational wave background. The sum of all the gravitational waves from all the supermassive black hole mergers that have occurred since the universe began, arriving at Earth as a stochastic hum in the fabric of space-time that makes the galaxy-sized detector formed by the pulsar timing array ring almost imperceptibly. The detection of this background is direct evidence that galaxy mergers, including the mergers of the supermassive black holes they contain, are real, common, and powerful. The universe's largest collisions leave their mark not in electromagnetic light, but in the geometry of space and time itself. Now let us talk about what galaxy mergers do to the galaxy's shapes, because the morphological transformation is one of the most dramatic and visually compelling aspects of a merger. And it tells us something profound about how the universe's gallery of galaxy types has been assembled. Most galaxies in the relatively nearby universe, within 1 billion light years or so, fall into two broad categories: spiral galaxies, like the Milky Way and Andromeda, with their organized disks, spiral arms, and ongoing star formation, and elliptical galaxies, which have no disk, no spiral arms, no ongoing star formation, and are instead smooth, roughly ellipsoidal distributions of old stars. Elliptical galaxies are particularly common in the dense environments of galaxy clusters, where the rate of galaxy-galaxy interactions is high. Small, irregular galaxies also exist: dwarf galaxies, irregular galaxies with no clear structure, but the two dominant types are spirals and ellipticals. The question of where elliptical galaxies come from was a major unsolved problem in observational astrophysics for decades. Ellipticals cannot form directly from the collapse of gas in the same way spirals do, because the formation of a disk requires the conservation of angular momentum in a rotating gas cloud, and the organized rotation of a disk is destroyed by any process that randomizes stellar orbits. Ellipticals have no organized rotation. Their stars move in essentially random orbits, producing the smooth, featureless distribution we observe. How do you make a galaxy full of stars moving in random orbits? The answer is galaxy mergers. When two spiral galaxies collide and merge, the organized rotation of their disks, the regular circular orbital motion of the stars in the disk plane, is destroyed. The collision imparts angular momentum changes to the stars, and the tidal distortions and gravitational interactions of the merger scramble the orderly disk orbits into the randomized anisotropic distribution that characterizes an elliptical. The starburst triggered by the merger consumes the gas, so the merged object has less material for future disk formation, and the stellar feedback and AGN feedback, which we will discuss in a moment, heat and expel remaining gas. Further suppressing star formation. The result, after the merger is complete, and the system has relaxed to a new dynamical equilibrium, is a galaxy with no disk, no spiral arms, no ongoing star formation, and a stellar population made up of the old stars of the progenitor spirals, plus the billions of stars formed in the starburst, an elliptical galaxy. This merger hypothesis for elliptical galaxy formation, that ellipticals are the remnants of merged spiral pairs, is now the standard picture in observational cosmology. The evidence is overwhelming. Elliptical galaxies show subtle tidal streams, shells, and fine structure in deep imaging, the fossil remnants of tidal debris from ancient mergers, still visible billions of years after the merger was completed. The stellar populations of ellipticals show the chemical signatures of a starburst, enhanced ratios of alpha elements like oxygen, neon, and magnesium relative to iron, which is the chemical signature of rapid star formation, because alpha elements are produced primarily by core collapse supernovae, which respond quickly to a starburst, while iron is produced primarily by type Ia supernovae, which respond on a delay of about 1 billion years. The kinematics of elliptical stellar populations, show the partially randomized orbital distribution expected after a major merger. And simulations, N-body and hydrodynamic simulations of merging spiral pairs, reproduce the morphology, kinematics, and stellar populations of observed ellipticals with remarkable accuracy. One of the most striking byproducts of major galaxy mergers is the formation of massive globular clusters. Globular clusters, dense, spherical collections of hundreds of thousands to millions of stars, gravitationally bound and orbiting the galaxy at large, radii, are among the oldest structures in normal galaxies, with ages of 10 to 13 billion years. Relics of the universe's early star-forming epoch. But young globular clusters, massive star clusters formed within the last few 100 million years, are found preferentially in starburst and merging systems. The superstar clusters in the antennae, resolved by Hubble and JWST, are young globular clusters in the process of formation, dense, massive, gravitationally bound stellar systems born in the intense gas compression of the merger-driven starburst. Many of these young clusters will disperse over time. They are too loosely bound to survive the tidal disruption of the galactic environment, but the most massive and compact ones will survive for billions of years, eventually becoming old globular clusters that future astronomers will study as relics of the merger that formed them. The globular cluster population of a galaxy is therefore a fossil record of its merger history. Galaxies that experienced more major mergers have richer, more massive globular cluster systems. The most massive elliptical galaxies have spectacular globular cluster systems containing tens of thousands of clusters, each one a billion-year-old remnant of a starburst triggered by one of the mergers in the galaxy's assembly history. Reading the globular cluster population of a galaxy is reading the ledger of its violent past. The chemical enrichment of galaxies through mergers and starbursts is another profound legacy. The massive stars formed in merger-driven starbursts, the O and B stars, 20 to 100 times the Sun's mass, have lifetimes of only a few million years before exploding as Type II supernovae. Each explosion ejects several solar masses of heavy elements: carbon, oxygen, neon, magnesium, silicon, iron, into the surrounding interstellar medium. A starburst forming stars at 1,000 solar masses per year produces roughly 10 supernovae per year, 10 times the Milky Way's current rate. The interstellar medium is rapidly enriched. The gas available to the next generation of stars and planets is richer in heavy elements, richer in the raw materials for rocky planets, richer in the chemical substrates for biological complexity than the comparatively metal-poor environment of a quiescent, isolated galaxy. Galaxy mergers are, in this sense, engines of chemical evolution, accelerating the production and dispersal of heavy elements, driving the universe's chemical evolution faster in their aftermath than it would proceed without them. The universe is in a profound sense a cannibalistic place. The large elliptical galaxies that dominate the cores of galaxy clusters, the most massive stellar systems in the known universe, containing trillions of stars, spanning millions of light years, are built entirely from the consumed remnants of smaller galaxies. The most massive elliptical galaxies, the brightest cluster galaxies, have grown to their current enormity through a long history of mergers, first with comparable-sized companions, then with the smaller galaxies that fell into their gravitational potential and were absorbed. This process, hierarchical galaxy growth, in which larger structures are assembled from smaller ones through gravitational accretion and merging, is the dominant mode of structure formation in the universe, operating at every scale from individual galaxies to galaxy clusters to the great cosmic web of filaments and voids that is the universe's largest structure. Now let us address the role of the supermassive black hole directly, not just as a participant in the merger, but as an active agent in shaping what happens during and after it. Because the merger does not just deliver two black holes to each other, it feeds them. The inflow of gas toward the galactic center during a merger, driven by the tidal torques that remove angular momentum from the gas, allowing it to fall inward rather than continuing to orbit at large radii, dramatically increases the supply of material available to the central black hole. The black hole accretes this gas, growing in mass and in luminosity, and the accretion process, matter falling into the black hole's deep gravitational potential well, releasing gravitational potential energy as heat and radiation with an efficiency approaching 10% of the rest mass energy, produces an active galactic nucleus, or AGN. When an AGN is particularly luminous, when the accretion rate is high and the released energy is enormous, it is called a quasar, a quasi-stellar object. So called because the energy released in the accretion process can be so intense that it outshines the entire stellar population of the galaxy by factors of hundreds to thousands, making the galactic nucleus appear as a bright point of light, similar in apparent brightness to a nearby star, despite being at distances of billions of light years. The discovery of quasars in the late 1950s and early 1960s is one of the most dramatic episodes in modern astronomy, and it is worth recounting in some detail, because the objects were so anomalous that understanding them required a complete rethinking of the energy scales available in the universe. Radio astronomers surveying the sky in the 1950s found a number of compact radio sources of radio emission that were unresolved, point-like, the way stars appear point-like compared to extended galaxies. When optical astronomers tried to identify these radio sources by finding the optical objects at their positions, they found star-like objects, blue, unresolved, with optical spectra unlike any known type of star. The spectra showed bright emission lines, but the lines could not be identified with any known element at the expected wavelengths. The breakthrough came in 1963, when Martin Schmidt of the Palomar Observatory was studying the spectrum of a radio source called 3C273, a bright, star-like object that had been precisely located by radio astronomers. Schmidt noticed that the pattern of emission lines in the spectrum, though at entirely wrong wavelengths, had the right spacing and intensity ratios to be the Balmer series of hydrogen, the familiar spectral lines of hydrogen emission, but shifted dramatically to longer, redder wavelengths. The redshift was approximately 0.158, meaning that 3C273 was receding from us at 15.8% of the speed of light due to the cosmic expansion, placing it at a distance of roughly 2 billion light years. At that distance, the optical luminosity of 3C273, which had been measured and found to be comparable to a bright nearby star, implied an intrinsic luminosity of roughly 4 × 10⁻113 solar luminosities, 40 trillion times the luminosity of the Sun, or roughly 100 times the luminosity of the entire Milky Way, from an object smaller than a solar system. Schmidt's measurement broke the problem wide open. Within months, Other quasi-stellar radio sources, all started, quickly abbreviated to quasars, were found to have similar or larger redshifts, placing them at cosmological distances and implying luminosities that no stellar process could account for. The entire energy output of 1 trillion stars from a region light days across. The only physically plausible energy source was gravitational accretion onto a supermassive black hole, the release of gravitational potential energy as matter fell into the deepest potential well available in nature. The calculation was straightforward. A black hole accreting matter at a few solar masses per year, converting 10% of the infalling mass to energy, produces exactly the luminosities observed. A stellar mechanism producing the same power would require a stellar cluster so massive and so compact that it would inevitably collapse to a black hole anyway. Quasars were powered by accretion. An accretion required a supermassive black hole. The most luminous quasars release more energy per second than 1 trillion suns, 10 or 2 solar luminicities, from the region smaller than the solar system. Quasars are most abundant at a redshift of approximately 2 to 3, corresponding to a time when the universe was about 2 to 3 billion years old, precisely when the merger rate of galaxies was highest, because the universe was denser and galaxy encounters were more frequent. The connection between mergers and quasar activity is direct. Mergers supply the gas that feeds the black hole. The black hole blazes. The Aegean feedback extinguishes both the quasar and the starburst that accompanied it. The result, well documented in observations, understood theoretically, reproduced in simulations, is a self-quenching mechanism for galaxy growth. The merger provides gas to both the starburst and to the black hole. The starburst forms stars rapidly. The black hole grows rapidly and becomes a quasar. The quasar's energy output, in jets and radiation-driven winds, heats and expels the remaining gas. The starburst ends because the gas is gone. The quasar dims because its fuel supply is exhausted. The galaxy settles into a red and dead state, a massive elliptical galaxy with no ongoing star formation, an old stellar population reddening as its massive blue stars age and die, and a now dormant supermassive black hole sitting quietly at the centre, growing only through the rare trickle of gas that makes it past the depleted interstellar medium. There is a remarkable correlation that has been measured in every large survey of galaxy properties, and it connects the mass of the central supermassive black hole to the mass of the galaxy's stellar bulge with a precision that implies a deep physical connection between the two. The M-sigma relation, first clearly established in 2000, shows that the mass of a galaxy's central black hole is approximately 0.2% of the mass of the stellar bulge, a proportionality that holds across many orders of magnitude in galaxy mass. From small ellipticals with million solar mass black holes to giant ellipticals with 10 billion solar mass monsters. This tight correlation cannot be a coincidence. The black hole and the bulge must be growing together, regulated by a common feedback process. The Aegean feedback mechanism, the quasar-driven expulsion of gas that simultaneously ends the black hole's rapid growth and the bulge's starburst, is the most natural explanation for this co-evolution. The merger triggers both. The merger-driven Aegean feedback ends both. And the final ratio of black hole mass to bulge mass is set by the balance between accretion efficiency and feedback efficiency, a balance that apparently produces the same 0.2% ratio across an enormous range of galaxy masses and merger histories. This co-evolution of black holes and galaxies through mergers is one of the central themes of modern extragalactic astronomy. and it means that the supermassive black holes in galaxy centers are not passive passengers in galaxy evolution. They're active regulators, capable of shutting down star formation in an entire galaxy through the mechanical and radiative energy they deposit in the surrounding gas. The black hole mass in the Milky Way today, 4.15 million solar masses, is small compared to the black holes in massive ellipticals, precisely because the Milky Way has not undergone a major merger in its recent history. After the Andromeda collision, when the two galactic nuclei merge and the combined mass of both black holes feeds on the tidally disrupted gas of the encounter, the resulting black hole will be considerably more massive, perhaps hundreds of millions of solar masses, and the AGN feedback it produces will shape the subsequent evolution of Milkomeda in exactly the way we have described for other merged systems. This AGN feedback mechanism is one of the most important processes in the physics of galaxy evolution. And it is why the most massive galaxies in the universe, the giant ellipticals at the centers of galaxy clusters, are not falling stars today, despite containing vast amounts of hot gas in their surrounding halos. The hot gas, observable in X-ray emission from its thermal radiation, cannot cool efficiently enough to form stars, partly because AG and jets from the central black hole periodically heat it, preventing the cooling that would be necessary for star formation to resume. The black hole, dormant for most of its life, stirs occasionally when a small amount of gas trickles inward, produces a brief flash of AGN activity, heats the surrounding medium, and returns to quiescence. It is a feedback loop that regulates the temperature of the gas in galaxy clusters on scales of millions of light years, governed by a black hole whose event horizon is measured in astronomical units. Now, let us bring all of this home, literally. Let us talk about the collision that is going to happen to our own galaxy, in our own backyard, in a finite and calculable future. Let us talk about the Andromeda Milky Way merger and what it means for everything in it, including, potentially, the descendants of life on Earth. The Andromeda Galaxy, Messier 31, the nearest large galaxy to the Milky Way, at approximately 2.537 million light-years, is approaching us, not slowly, not imperceptibly. At approximately 110 kilometers per second along the line of sight, plus a transverse component that Hubble Space Telescope and Gaia measurements have pinned down precisely enough to project the merger trajectory in three-dimensional space. The story of how we know this collision is coming, how we measured Andromeda's velocity precisely enough to determine that it is bound to merge rather than merely pass by, is itself a story of increasingly precise measurement across 2 centuries. William Huggins first measured the radial velocity of Andromeda in 1867 using the Doppler shift of its spectral lines, finding that Andromeda was approaching Earth at about 50 kilometers per second, making it one of the few objects in the sky moving toward rather than away from us. This measurement was refined over the following century, eventually settling at the current value of about 110 kilometers per second of approach along the line of sight. But a radial velocity alone does not tell you whether 2 galaxies will merge. 2 galaxies approaching each other radially might have sufficient tangential velocity to miss each other, entering a hyperbolic or elongated elliptical orbit, rather than a merging one. The critical measurement was of Andromeda's transverse velocity, its motion across the sky perpendicular to the line of sight. This is far harder to measure than the radial velocity because even at Andromeda's relatively modest distance of 2.537 million light-years, the transverse motion over any human-relevant timescale is too small to directly observe as a change in position. The measurement required the extraordinary astrometric precision of the Hubble Space Telescope, making multiple observations of the same stars in Andromeda over a period of years and measuring the cumulative proper motion, the tiny angular shift across the sky, to constrain the transverse velocity. The result, published by Sang-Mo Tony Son and collaborators in 2012, was a transverse velocity of roughly 17 kilometers per second, far smaller than the radial approach velocity, implying an orbit that is overwhelmingly radial, heading almost directly toward us. The combined orbital calculation, including both the radial and transverse components, conclusively demonstrated that the Milky Way and Andromeda are on a collision course, with a first close passage in about 3.75 to 4.5 billion years, depending on the precise mass models used. A subsequent Gaia measurement of Andromeda's proper motion, published in 2019, confirmed the Hubble result with higher precision, tightening the orbital parameters and confirming the merger timeline. This is a remarkable piece of knowledge. We know that our galaxy will collide with Andromeda in a calculable number of years, using measurements made by spacecraft operating in the 21st century, with precision sufficient to characterize the orbital geometry of two objects separated by 2.5 million light-years. The measurement of Andromeda's proper motion, the angular shift of distant stars across the sky over a period of a few years, required astrometric precision of tens of microarcseconds, equivalent to measuring the apparent position of a coin on the moon to within the width of a human hair. The knowledge that the Milky Way is doomed to merge is not ancient cosmological speculation. It is a precision measurement made within living memory, with instruments whose operational lifetimes are measured in years and decades. The current best estimates, from detailed N-body simulations constrained by Hubble and Gaia proper motion measurements, predict a first close passage of the two galactic centers in approximately 4.5 billion years, with the two nuclei completing their merger and coalescing into a single system in roughly 6 to 8 billion years. The resulting merged galaxy, sometimes called Milkomeda by cosmologists, will be a large elliptical galaxy formed from the combined stellar populations of the Milky Way, Andromeda, and whatever smaller satellite galaxies have been absorbed in the interim. The Milky Way and Andromeda are not isolated. Each is attended by a system of satellite galaxies, smaller, less massive galaxies gravitationally down to the larger host and orbiting it at distances of up to a few 100,000 light-years. The Large and Small Magellanic Clouds, visible from the southern hemisphere as detached patches of the Milky Way, are the two largest Milky Way satellites. ALMC has about 10 billion solar masses in stars, the SMC about several billion. Andromeda's satellite system includes M32, M110, and dozens of smaller dwarf galaxies. All of these satellites are participants in the merger, some of them pre-merging with their hosts before the main collision occurs, others being tidally disrupted and incorporated during the merger itself, and still others being flung to large orbits or entirely out of the merged system by the tidal forces of the encounter. The question most people want answered when they hear about the Milky Way-Andromeda collision is the same question they ask about any galaxy collision. What happens to us? What happens to the Sun? What happens to the Earth? And the answer, informed by everything we have discussed about the emptiness of galaxies and the non-collisional nature of stellar populations in a merger, is both anticlimactic and profound. The Sun will almost certainly survive the merger without physical harm. The probability of the Sun's direct physical collision with any star in the Andromeda Galaxy is, as we have established, essentially zero. Even in the densest regions of the merged system, in the galactic center, where the stellar density is much higher than in the disk, the probability of a direct stellar collision over the entire merger timescale remains less than 1% for any given star. The Sun, sitting in the relatively sparse outer disk of the Milky Way, is unlikely to be driven into a denser region by the merger dynamics. In-body simulations of the Milky Way Andromeda merger show that most disk stars end up in the outer regions of the merged elliptical, not in the dense central regions. The Sun is most likely to spend the merger period orbiting in the combined tidal field of the merging system, gradually relocating through the gradual modification of its orbit by the changing gravitational potential to a new position in the merged galaxy, but never approaching a density of stars high enough to produce a significant collision risk. The Earth's orbital stability is a different question, and it is less reassuring than the stellar collision story. The Sun's orbit through the combined gravitational field of the merging galaxies will be significantly modified. Net-body simulations by T.J. Cox and Abraham Loeb, whose 2008 paper on the Milky Way Andromeda merger is among the most cited treatments of this topic, found that there is a roughly 12% chance that the solar system is kicked out of the Milky Way disk entirely during the merger, into a wide, eccentric orbit through the outer regions of the forming elliptical, and a small but non-zero chance that the solar system ends up closer to the galactic center, where higher stellar density and the radiation environment of the eventual quasar phase could pose hazards. A most likely outcome for about 85% of Milky Way disk stars is that the Sun ends up in the outer regions of the merged elliptical, far from the violent central regions, with its orbit modified but its planetary system intact. But we are projecting 4.5 to 8 billion years into the future, and the Sun itself has a limited lifespan. In 4.5 billion years, approximately when the first close passage of the Milky Way and Andromeda occurs, the Sun will be roughly 9 billion years old, approaching the end of its main sequence lifetime. In about 5 billion years from now, the Sun will exhaust its hydrogen fuel and begin expanding into a red giant, swelling to perhaps 100 to 200 times its current radius, potentially engulfing the Earth, and certainly vaporizing any surface oceans or atmosphere that might remain. The fate of Earth is sealed by the Sun's evolution, long before the Milky Way Andromeda merger completes. Whatever life exists on Earth, or on any Earth-like planet in our solar system, will have to contend with the Sun's aging before the merger is cosmically spectacular. Why say MB? The Sun's red giant phase is personally relevant. This does not mean the merger is irrelevant to the question of life. The starburst triggered by the collision will produce new generations of stars and potentially new planetary systems, scattered through the merged galaxy. The increased supernova rate during the starburst phase will enrich the interstellar medium with heavy elements, carbon, oxygen, silicon, iron, the elements of rocky planets and biochemistry, at an elevated rate, potentially seeding future planetary systems with a richer chemical inventory than the current epoch interstellar medium provides. The merger is, in a sense, the factory that produces the conditions for future life, even as it may disrupt the conditions for current life. Galaxy mergers do not just build galaxies, they build the chemical infrastructure for future planetary systems and, indirectly, for future biospheres. The quasar phase that accompanies the final merger of the two galactic nuclei, when the Sagittarius A and the Andromeda black hole coalesce and their combined accretion sends a quasar blazing at the center of Milky will be visible as an extraordinary bright nucleus, perhaps as bright as a full moon in the sky of any planet within a few thousand light years of the galactic center. For planets in the outer galaxy, the quasar nucleus will be a brilliant point of light in the sky, brighter than any star, a new feature of the night landscape for however long the quasar phase lasts. The radiation from the quasar, the ultraviolet and X-ray photons streaming outward, will not be hazardous at the distances typical of disk stars, because the inverse square law dilutes the radiation enormously by the time it reaches the outer galaxy. The energy that was so intense near the nucleus becomes manageable radiation background at galactic distances. Life on outer galaxy planets would see the quasar. It would not be threatened by it. It is worth stepping back from the specifics of the Andromeda collision and considering the broader context, the merger history of the Milky Way itself, which is not only a future event, but a past one, written in the archaeology of the galaxy's stellar populations. The Milky Way has been merging with smaller galaxies throughout its history. The smooth stellar halo that surrounds the Milky Way disk, the diffuse population of old metal-poor stars that orbit the galaxy in roughly spherical, often highly eccentric orbits, is the accumulated debris of dozens of smaller galaxies that fell into the Milky Way and were tidally disrupted over the past 10 billion years. The Gaia satellite has been the instrument that revealed this history in unprecedented detail, mapping the positions, velocities, and chemical compositions of nearly 2 billion stars and allowing researchers to identify groups of stars with similar orbital characteristics, the dynamical fossils of ancient mergers. The most spectacular of these ancient mergers is now called Gaia Enceladus, or the Gaia Sausage, a dwarf galaxy, roughly the mass of the Large Magellanic Cloud, but collided with the proto-Milky Way approximately 8 to 11 billion years ago. The identification came from a striking feature in the distribution of stellar velocities. A population of stars with high radial velocities moving rapidly toward and away from the galactic center, but low tangential velocities barely rotating around the galaxy, forming an elongated, sausage-shaped distribution in velocity space. This kinematic signature is the characteristic imprint of a head-on or nearly head-on merger. The stars of the merging galaxy, stripped from their original orbits and deposited into the Milky Way's halo, retain their radial velocity distribution from the merger and produce the sausage shape in velocity space. The chemical compositions of these stars, consistent with the enrichment history of a small galaxy, with lower metallicity and different elemental ratios than comparable age Milky Way stars, confirm their extragalactic origin. The identification of Gaia Enceladus required matching the positions, velocities, and chemical compositions of individual stars across the entire sky, a task that was impossible before Gaia provided the astrometric and photometric precision needed to separate the different stellar populations. Hilma Koppelman, Amina Helmi, and collaborators at the University of Groningen first identified the structure in 2018, and the result was rapidly confirmed and extended by multiple groups using the same Gaia data release. The name Enceladus comes from the Greek myth of the giant who was buried under the island of Sicily after being defeated by the goddess Athena, an ancient structure buried under the mass of the Milky Way, detectable only by the kinematic fingerprint it left in the stellar populations it contributed. The Gaia Enceladus merger was not just a minor addition to the Milky Way's outer halo, it was a major event in the Milky Way's structural history. Simulations suggest that the merger was energetic enough to heat and thicken the Milky Way's disk, puffing up the thin disk into the thick disk, and to trigger a significant episode of star formation in the proto-Milky Way, leaving behind a population of old, metal-rich stars in the galaxy's inner halo and thick disk that are among the oldest stars in the current Milky Way. The thick disk of the Milky Way, the kinematically hotter, older, more metal-poor disk population that sits above and below the thin disk, may therefore be at least partly a product of this ancient merger. Its stars heated from their originally thin disk orbits by the energy deposited by the infalling Gaia Enceladus galaxy. The Milky Way structure is a fossil of this collision. Other ancient mergers have been identified in the Gaia data. The Sequoia Galaxy, another dwarf merger with a prograde orbit, the Helmy Streams, a disrupted satellite, the Pontus Galaxy, Kraken, potentially the most massive of the Milky Way's ancient merger partners, predating even Gaia Enceladus, with a total mass perhaps 2 or 3 times that of Gaia Enceladus, and an interaction so ancient, roughly 11 billion years ago, when the Milky Way was only a few billion years old, that its debris is buried in the most ancient stellar populations of the inner halo and bulge. Each of these was a smaller galaxy that fell into the growing Milky Way, was tidally shredded, and had its stars deposited into the halo and thick disk, contributing to the hierarchical assembly of the galaxy we live in. The Milky Way grew to its current size not from the smooth collapse of a single gas cloud, but from the cannibalistic accumulation of smaller galaxies, each collision adding stars, dark matter, and occasionally triggering new waves of star formation in the growing galaxy. There are ongoing mergers as well, not yet complete. The Sagittarius Dwarf Spheroidal Galaxy, discovered in 1994 by Rodrigo Ibata, Mike Irwin and Gerard Gilmore at the Institute of Astronomy in Cambridge, is currently being tidally disrupted by the Milky Way's gravity. Its stars being progressively pulled out into a stellar stream that wraps around the Milky Way multiple times, a great ribbon of stars encircling our galaxy in a polar orbit. The Sagittarius stream extends over 360 degrees around the sky and contains hundreds of millions of stars drawn from the Sagittarius dwarf over the last several billion years of repeated close passages. What remains of the Sagittarius dwarf core is still detectable as a compact stellar overdensity in the direction of the constellation Sagittarius, gradually being consumed, its stars being liberated into the Milky Way's halo, one orbit at a time. In a few billion years, the Sagittarius dwarf will be fully disrupted and absorbed, its stars indistinguishably mixed into the Milky Way halo, its identity as a separate galaxy erased. The Large Magellanic Cloud, currently orbiting the Milky Way at about 160,000 light-years and visible to the naked eye from the southern hemisphere as a bright, detached patch of the Milky Way, is also a temporary companion. Recent analysis of Gaia proper motion data suggests that the Large Magellanic Cloud is on its first infall into the Milky Way, having come from a large distance and been captured only relatively recently in cosmic terms, and that its current orbital trajectory will likely lead to a merger with the Milky Way in a few billion years, well before the Andromeda collision, or, alternatively, to a close pass that sends it back out to large orbital radius. The interaction between the Milky Way and the LMC is already producing detectable tidal effects. The LMC's mass is large enough to cause a measurable displacement of the Milky Way's dark matter halo from its centre of mass, a wobble that has been measured in the positions and velocities of distant halo stars, and to drag a large stream of gas from both the LMC and SMC into intergalactic space, the Magellanic Stream, a ribbon of hydrogen gas extending over 200 degrees across the southern sky. Our galactic home is not a static, isolated structure. It is an active, dynamic system, currently accreting satellite galaxies, distorted by the gravitational pull of its largest companion and heading toward a major collision in the far future. The Milky Way we live in is the product of all its past mergers, shaped by the ancient collision with Gaia Enceladus and dozens of smaller mergers, and it will be transformed by future mergers with the LMC and then with Andromeda into something qualitatively different from what it is today. The history of our galaxy is a history of collision, just as the history of all galaxies is a history of collision. There is no galaxy that has not been shaped by mergers. There is no stellar population that is not, at some level, the product of a collision. This history of accretion and merging is not unique to the Milky Way. It is the universal history of all large galaxies. The cosmological model of galaxy formation, lambda, cold dark matter, or lambda, CDM, the standard model of modern cosmology, predicts that all large galaxies grew through exactly this process of hierarchical assembly. Small dark matter halos collapsing first, hosting the first stars and galaxies, then merging into progressively larger halos that hosted progressively larger galaxies, building up the structure of the universe from the bottom up. The observational evidence for this picture is overwhelming. The Milky Way's halo structure, the morphology of merging systems like the antennae, the properties of elliptical galaxies, the quasar luminosity function and its evolution with redshift, the detection of the gravitational wave background from supermassive black hole mergers. All of these are consistent with the hierarchical assembly picture and inconsistent with any scenario in which large galaxies formed monolithically without merging. The universe builds from small to large. It assembles complexity through collision. Every large galaxy is a graveyard of smaller ones, and every elliptical galaxy at the center of a cluster is the greatest cannibal of all, having consumed companions for billions of years, grown fat on their stellar populations, and now presiding over a cluster that is itself a gravitational trap from which no galaxy can ultimately escape. The cluster's central galaxy will continue to grow, slowly, merger by merger, until the universe's accelerating expansion and the final decay of all stellar populations leave it as the last coherent structure in an otherwise empty and cooling cosmos. Before we close, let us return to the visual and emotional impact of what we have been discussing. Galaxy collisions are among the most visually spectacular phenomena in observational astronomy, and the images obtained by the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories over the past 3 decades have made them available to anyone with an internet connection. The Antennae Galaxies, the Mice Galaxies, NGC 4676, 2 spirals in the process of a close encounter, trailing long tidal tails that resemble the tails of 2 mice. The Cartwheel Galaxy, ESO 350-40, a ring galaxy formed when a smaller companion punched directly through the center of a larger spiral, sending a ring of star formation propagating outward like a wave, observable as a blazing ring of young blue stars nearly 150,000 light-years across, created by a collision. The Tadpole Galaxy, UGC 10214, a spiral galaxy trailing a 280,000 light-year tidal tail of blue stars, drawn out by the passage of a compact intruder galaxy. The Stefan's Quintet, HCG 92, a compact group of 5 galaxies in various stages of interaction. One pair, apparently, in the early stages of merging. The whole complex, a laboratory for studying the effects of repeated galaxy-galaxy encounters on gas, star formation, and AGN activity. Each of these objects, each of these images, is a moment frozen in what is, by cosmic standards, a fast event. The antennae are visible to us at this particular stage of their merger because we happen to be observing them now, roughly 45 million years after the first close encounter between the two spirals. In another 100 million years, they will look completely different, deeper into the merger, the tidal tails more dispersed, the central starburst fading. In a billion years, they will have coalesced into an elliptical galaxy, and the beautiful two-arm spiral structure will be gone, replaced by the smooth, featureless luminosity distribution of the merged system. We are catching them at a cosmologically brief moment, the way a photograph catches a wave at the moment of breaking, a moment of maximum drama, maximum visual complexity, before the turbulence settles into calm. This is also true of the Milky Way Andromeda merger. In 4.5 billion years, the first close passage will be occurring. The tidal tails will be stretching into intergalactic space. The starburst will be igniting. The night sky, as seen from any planet surviving in the disk of either galaxy, will be utterly transformed. The diffuse smear of the Milky Way, familiar to humans who have lived on Earth for 300,000 years, will be replaced by a night sky so full of young, luminous stars that there will barely be darkness between them. The star formation rate in the merged system will be dozens of times the current rate, and the sky will glow with the light of billions of new stars born in the collision of two ancient and noble spirals. And then, over hundreds of millions of years, the starburst will fade, the tidal tails will disperse, the two galactic nuclei will spiral together under dynamical friction and eventually merge in a brief, brilliant quasar flash. The quasar will dim as its fuel is exhausted. The merged system will relax into the smooth shape of an elliptical galaxy, its stellar populations aging and reddening, its star formation ended, its disk structure long since scattered. Milkomeda will take its place among the large elliptical galaxies of the local group, the merger of two small spirals, now a single large elliptical, cooling slowly toward the distant future of a universe whose expansion has already carried most other galaxies beyond the observable horizon. None of the humans alive today will see any of this. The merger begins in 4.5 billion years, longer than the current age of the Earth. But we know it is coming, precisely because we have measured the velocity of Andromeda with enough accuracy to project the trajectory, because we have built simulations of the merger that show what it will look like at each stage, because we have studied 100 other merging systems and read in their morphologies and stellar populations the signature of what this collision will produce. We know the future of our galaxy in a way that no human civilization before the 20th century could have imagined, and the knowledge is both humbling and thrilling. But the story of the Milky Way Andromeda collision does not end with the formation of Milkomeda. It continues far into the future, and that far future has its own character that is worth considering. Because the merger of the Milky Way and Andromeda into a single elliptical galaxy is not the end of the gravitational story for the local group, the collection of approximately 50 galaxies bound together by their mutual gravity in the region surrounding the Milky Way and Andromeda. The local group has a diameter of roughly 10 million light-years and contains two large spiral galaxies, the Milky Way and Andromeda, plus the triangular galaxy M33. From the smallest spiral, about 2.7 million light-years away, at about 1/10 the mass of Andromeda, and dozens of dwarf galaxies including the Magellanic Clouds, the Sagittarius Dwarf, Leo 5 and Leo 2, and many others identified in recent surveys. The entire local group is gravitationally bound. Despite the general expansion of the universe, the mutual gravitational attraction of all these galaxies is sufficient to overcome the cosmological expansion within the local group volume. And the local group will not disperse even as the rest of the universe expands away from it. As Milky forms from the Milky Way Andromeda merger, it will become the dominant gravitational influence in the local group. The smaller galaxies orbiting it, the dwarf companions, the satellite galaxies, will gradually spiral in under dynamical friction and be absorbed into Milky over tens of billions of years. Mil-33, the Triangulum Galaxy, may itself participate in the merger, either directly with Andromeda before the main Milky Way Andromeda encounter, or later with the already merged Milky. Simulations of the local group's long-term evolution suggest that within roughly 100 billion years, about 7 times the current age of the universe, essentially all the galaxies of the local group will have merged into a single giant elliptical galaxy, a local group elliptical, or Milky in its final, most massive form. This ultimate merger will have absorbed every star, every planet, every stellar remnant in the local group into a single, slowly cooling, gravitationally relaxed system. Meanwhile, the universe's accelerating expansion will have carried every other galaxy group and cluster beyond the observable horizon. The local group elliptical will be, for all practical purposes, the only galaxy in the observable universe. Not because other galaxies have ceased to exist. They will still be out there, in their own local groups and clusters, following their own merger histories, but because the expansion of space will have carried them beyond the point from which light can ever reach us. The sky, from within the local group, elliptical in the far future, will show no other galaxies, just stars, the stars of the merged local group, growing cooler and redder as their nuclear fuel is consumed, slowly transitioning through the stages of stellar evolution toward their ends as white dwarfs, neutron stars, and black holes. The universe will appear, to any observers persisting in that far future, to be nothing but a single island of stars in an otherwise empty and accelerating void. And eventually even those stars will die, and the merged galaxy will be a dark cloud of stellar remnants, a graveyard of 100 billion suns, orbiting a common centre of mass, in a cosmos too cold and too empty for any new stars to form. This is the ultimate legacy of galaxy mergers, not catastrophe, not destruction, but a slow, patient, gravitationally driven consolidation of matter into larger and larger structures, until the expansion of the universe outpaces the process and the last gravitationally bound systems, the local groups and clusters, are left as isolated islands in an infinite expanding ocean, consuming themselves from within, growing quieter and darker and colder until there is nothing left of the brilliant, blazing, merger-driven cosmos that assembled itself in the first few billion years after the Big Bang. The mergers we observe today, the antennae, the mice, the cartwheel, the dozens of interacting pairs cattle, that first solution, period arc tettle, are all episodes in the program. It seems to say that most of the stories will be held and torn with the planet of the sky. Each one is a moment in the hierarchical assembly of the universe's structure, a chapter in the construction of the large-scale architecture that the Big Bang left as mere quantum fluctuations, and that gravity has been amplifying into the cosmic web of filaments and voids, galaxy clusters and superclusters. That we observe today. Galaxy mergers are not occasional catastrophes interrupting the peaceful evolution of the universe. They are the mechanism. They are how the universe builds. Two galaxies approach. They distort each other with gravity. They pass through each other in a slow, majestic interpenetration, during which stars barely notice the passage. But gas is shocked and compressed into the nurseries of new stars. They separate briefly, trailing tidal tails, then fall back toward each other, drawn by the gravity that will not release them. They merge. The supermassive black holes spiral together and coalesce in a burst of gravitational waves. A quasar blazes. The gas is consumed or expelled. The star formation ends. The elliptical settles. And in the smooth, featureless glow of the merged system, billions of years of collision have been transmuted into billions of new stars, billions of new potential planetary systems. A new chapter in the universe's ongoing project of building structure from chaos, meaning from collision, cosmos from collision. The universe does not merely tolerate collision, it requires it. Every large galaxy, every ancient star, every heavy element beyond hydrogen and helium, all of it is the product of collisions, of the hierarchical assembly of small things into large things, through the patient, relentless work of gravity. Galaxies collide, not as an accident or a catastrophe, but as the central mechanism of the universe's creative process. They collide, and in the collision, they become more than they were.